Hi everybody, and welcome to Lecture 4 of Digital VLSI Design at Bar-Ilan University. Today we'll start Lecture 4, Logic Synthesis Part 2. In this lecture we'll continue our discussion of logic synthesis that we started last time. So, just a reminder of what we've discussed so far. Actually, we haven't discussed too much about logic synthesis. We briefly discussed compilation, syntax analysis, and then we really dove down into the down and dirty of standard cell libraries with the whole library definition part. At this point, we've loaded our design into the synthesizer, we've loaded our standard cell library and IPs. Now we can move on to the brains of the synthesis process. So all of this stuff is what we're going to discuss today until we finish synthesis. Reporting we'll discuss next time. So we start with Boolean minimization. This includes mapping to generics and libs, basics of Boolean minimization, BDDs, two-level logic, and Espresso. Thanks a lot to Rob Rutenbar, who gave a great course on Coursera, which I based a lot of my stuff on. So the next stage in our flow is elaboration and binding. So just a few words about what we're going to have happen at this stage, and then we'll go down into some of the algorithms that help us do this. So what we're going to do is we're going to take our RTL and we're compiling it into a Boolean data structure. That's called elaboration. During this elaboration, we also do what's called binding, which means we look for leaf cells that are not standard Verilog or VHDL primitives or commands. And we look for how we find what each of these things is, such as an SRAM or an IO cell or some sort of other IP that we need to find. We bind it, we point to it with our design. So that way we have actually a net list of standards of primitive gates, and we have our hard macros or our IPs that are instantiated inside our net list. Finally, we go through a Boolean optimization, and we try to minimize literals, as we'll discuss in a few seconds. So the resulting design is mapped into a generic netlist. So we have a whole bunch of generic gates that are internal to our synthesizer, AND gates, OR gates, and so forth. And but they're technology independent, so they're not in a certain process technology. They don't have certain drive strengths, etc. This is the core of synthesis and been a very central subject of research in computer science since the 80s. So this is a subject that has been researched a lot, and there's a lot of brains in it. I'm just going to discuss really a few points and a few basics that go into this. So here's a small illustration of the whole elaboration process. We started with our state machine that we drew up, and we knew how to turn it into some very specific RTL code. That was, we were able to stick it into a synthesizer and easily, almost straightforwardly, elaborate it into, here we have some flip-flops, some logic, some other flip-flops. We also have, which I don't have on the picture here, some input ports and maybe some output ports that go from the design. So our whole logic was actually, our whole state machine was turned into these flip-flops, this logic, and these ports. That completely described our sequential system. So again, the registers were inferred when our compiler went over the Verilog code and saw all the always at pos edge clock type definitions. It knew how that there should be a flip-flop there and was able to infer them. At all the assign statements and the always at star statements, it knew how to put these combinational bubbles in the middle. And the combinational bubbles are actually just Boolean logic. They're truth tables that say, okay, we have a whole bunch of variables. There can be a lot of variables, which the variables are the different points here. So the outputs of each of these inferred registers and the inputs to the design. And the outputs here, these Fs, are the outputs which go into output registers or endpoint registers, we'll call them later, and the outputs from the design. So now we have this Boolean logic, and what we're going to discuss now is optimization of the Boolean logic, and the first stage is what we call two-level logic. So we know that each of these output statements in our Boolean truth table can be described as a sum of products or product of sums. Okay, so here basically we have a sum of product representation. By the way, these different things have nothing to do with each other, they're just for the example, but we know that we can straightforwardly make a sum of products in a two-level logic form, and we're going to discuss how we can optimize this by reducing the number of literals that appear in the sum of products form. So two-level logic, as we said during elaboration, our primary inputs and outputs, our different ports, are defined, and the sequential elements, which are the flip-flops and latches, are inferred. Okay, this results in a set of combinational logic clouds with input ports and register outputs that are inputs to the logic, output ports and register inputs that are outputs of the logic, and we can describe the outputs as Boolean functions of the inputs. So, just for an example, we have here our literals. These are our inputs to the design. Again, they are output either from registers or their primary inputs to the design. And we have our output, which is either the input to another register or it's a primary output for the design. And we have some sort of a two-level logic here where we have our sum of products that is a bunch of AND gates and a single OR gate that connects them all. What we're going to do in two-level logic is we're going to try to minimize the number of literals. So when we discuss the Boolean logic, we count the number of literals here, or the number of times a certain input appears in our function. In the case of two-level logic, we just look actually at the number of letters we have that appear at the first level of the design. So here we can count the number of literals, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 literals. So we have 10 literals over here. And after some minimization algorithms, we have 1, 2, 3, 4, 5, 6, 7, 8 literals. So what we did is we actually were able to reduce the complexity of the logic, figuring that we have less gates or less complex gates. So there are many different structures that are used to represent the Boolean functions. Computational Boolean algebra is a very extensive, very well-researched subject, and a lot of it has dealt with this two-level logic minimization. So truth tables we know about, and we'll learn about a bit about binary decision diagrams here in this lecture. This is something called a cube. It's another type of a representation to use. You can do analytical things with equations and so forth. So two-level logic is what we're discussing now. And again, the reason being that we can take that combinational logic we have between the registers, between the inputs and the outputs, and we can represent it in two-level logic and start to reduce it. So how do we go about this two-level logic minimization? Everyone probably who's listening to this lecture learned about Carnot maps. So Carnot maps, for n inputs, it has 2 to the power of n entries, and our objective is to find the minimum prime cover where we can put these covers around the ones for a sum of products or the zeros for a product of sums. Okay, however, it's very difficult to automate this thing that we kind of do by looking at these Carnot maps and looking for the sum of products, especially once we go to higher dimensions. So here we have a total of 4 variables. If we want to add a 5th variable, we have to put another dimension, and more than 6 variables is very hard to do on a piece of paper, maybe even impossible. Okay, it's really hard to automate it in a computer algorithm as well. That's why Quine and McCluskey came up with the first real method for finding the prime cover of a Boolean equation, and there's an iterative process that goes, and it can be done in software. But the problem is that, again, once we get a lot of variables there, it takes a real long time to go and actually minimize a function with the Quine-McCluskey method. And if you ever did any Quine-McCluskey on a piece of paper, it's very tiring. So some Berkeley students, they were falling asleep while trying to solve a Quine-McCluskey exercise, and they really needed a shot of espresso. And they invented this Espresso heuristic minimizer. Okay, so the Espresso heuristic minimizer is the primary or the basic tool that is used for two-level logic minimization, and it starts with the sum of products solution, which we saw that we can arrive to pretty easily between the inputs to our combinatorial cloud and the outputs from our combinatorial cloud. What we do is we take 3 steps. We first expand, which means we make each cube as large as possible without covering a point in the offset. This generally increases the number of literals. In other words, we went from our solution to a worse solution. Then we have a stage called irredundant, And in irredundant, we go and we look for redundant cubes and we throw them out. All of this we're going to see in a minute illustratively, and it will become more clear. This removes smaller cubes whose points are covered by larger cubes. And finally, we have a stage called reduce, where the cubes in the cover are reduced inside. So Espresso is E and RR and another R, that's Espresso, okay? And so here's some pseudocode for this algorithm. So what we're gonna do is we're gonna have this do while loop. We're gonna iteratively reduce, expand, and irredundant. Keep on doing this as long as we're able to get to a better solution. We're gonna throw out solutions that are not better, and finally, at some point, we're gonna stop. This is a heuristic. It means that our new cover is going to be different from the initial cover. Okay, it may not be, or there's a good chance that it won't be better than our previous cover, but it's trying in different dimensions, and we can have many dimensions in our solution to apply this, and therefore we're going to get this different solution every time, and hopefully we'll find a better cover than the last time with fewer literals. So let's see this in action and understand what I was talking about. Okay, so we start with this SOP form, this sum of product form, and I'm just going to show it on 4 variables because that's easy to show on a piece of paper. Doing it in a higher dimension is hard to illustrate. Okay, so what we have is we have these 4 cubes here. 1, 2, 3, 4. We have 4 cubes here, and this is the function that we're describing. A bar C bar plus C bar D bar plus AC plus C D bar. And if we count, we have 8 literals here. Okay, 8 literals. So its initial set of primes found by steps 1 and 2 of the Espresso method. This is just the starting point that we're showing for the example. Okay, we have 4 primes. We have irredundant cover, but it's not a minimal cover. So what we're going to do, first of all, is we're going to do the reduce stage. Reduce stage means that we're going to take these covers and make them as minimal size as possible. So this cube of 4 and this cube of 4, they have some redundant or overlapping parts, so we can make one of them smaller. So we decided by some sort of a decision to make this this cube smaller, and therefore we have these 4 and we have these 2, and again here we decided between these 2 which one will cover these 2. We decided that this square will, so we made this one smaller. When we do that, which is the reduce, what we have now is this equation describing the same Boolean functionality. And as you see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 literals. So 10 literals, which is a worse solution. So we went backwards, in fact. Okay, that's not very good because what we wanted to do was get to a smaller number of literals, but bear with us. This was just one direction, one choice of what we did. In our next step, we have expand. So in expand, what we do is we choose randomly, or according to some other heuristic, how we're going to take all of those cubes we had and make them as big as possible. So what happened is that we expanded out this one to cover all these. We expanded out the one that was over here to cover these 2. We expanded out these ones to cover these 2, and we expanded out this to cover all of this. We arrived again at 8 literals, as you can see here. But it's a different solution. It's not the same solution as we had on the previous slide. Okay, and now we're going to do the irredundant stage over here. And at the irredundant stage, we're again going to look what we have here, and we see that this cube is completely covered by this cube and this cube, and therefore it is redundant. So we can just throw it away. And once we threw it away, we get to 3 covers, and we see that in the end there are only 6 literals in our solution, and we arrived at a better solution, and that was the goal of our whole heuristic. So remember that this was on only 4 variables, but once we have it on many dimensions, then every time that we do a reduce, expand, and irredundant, we're going to have a different solution, and we're going to see which one of them is going to be best. So that was 2-level logic minimization. And the thing is that we know that most of the time, we're going to have many levels of logic. If we remember, we've learned logical effort or how to drive a large load. It's often we're not going to usually have gates with high fan-ins. In fact, CMOS is usually limited to about a fan-in of 4 per gate. And as we increase the fan-in of a gate, our propagation delay gets worse. So we're usually going to have several stages, maybe many stages of logic, and not just 2-level logic solutions for any given Boolean equation. So when we want to take these 2-level logic and apply it, they don't make much sense because, again, we're going to usually want to have multi-levels of logic to balance the load and so forth, and also maybe take internal products and so forth from inside the logic. Therefore, we had to start a whole new optimization regime, which is known as multi-level logic minimization. We're not going to cover it. There are many algorithms. You can go to Rob Rutenbar's lectures to learn about some of them, or altogether research this on the web, or take a university course in these types of algorithms. But I just want to say that a lot of them are based on 2-level logic minimization and expansions of it. Anyway, there's no perfect method for it, all kinds of different heuristics. But let's see the potential of this in the next slide. Okay, so we have a following logic set. We have all kinds of equations. T1 equals A plus BC, T2 D plus E, T3 AB plus D, T4 equals these terms, T1 and T2 plus FG, T5 is T4H plus T2 plus T3, and F equals T5 bar. Now, when we look at this, when we want to count the terminals, we count all of these guys, all of the inputs to the different gates along the way, and so we can draw our different gates, and we can count, and we see that altogether letters, there's 17 literals. So for example, T1 and T2 are considered literals for the input to this gate, whereas at this level it would just be our inputs. Okay, so we had 17 literals, and if we play around this with Boolean algebra or with different types of heuristics that can be applied for multi-level logic minimization, what we come out with, or one of the possibilities we could come out with, is a different set, which if we look at it, it's exactly the function of f is equivalent to the function of f over here, but we only have it 13 literals, and that is considered, at least at this level of elaboration, as being a more optimal solution than the 17 literals. So this is what the point of multi-level logic minimization is going to do, what we're going to try to be doing along the way. I want to now just go into one of the structures that is used for storing Boolean logic, for storing truth tables inside a computer or in general, and it's called a binary decision diagram, or BDD, and it's very widely used throughout synthesis and throughout different algorithms that do all kinds of things on netlists. Okay, so BDDs are directed acyclic graphs that represent the truth table of a given function. So we take a truth table here, just some sort of a truth table with 3 inputs, x1, x2, and x3, and 1 output, which is called f, and we see the truth table over here, what each input state will provide. We can show a binary decision diagram which takes each one of these inputs in order, and so x1 is our first input. We put it at the first level, and what we get basically is these like layers. So this here is the layer of x1, this is the layer of x2, this is the layer of x3, and this is the layer of the outputs, okay, which is f. So it's very important to already notice that the ordering here is very important. So if we would write this function x2, x3, x1, or x3, x2, x1, or some other way, we would get a different BDD. Okay, so the ordering is important. So here we have x1, x2, x3, and what we do is we look at the root node, x1, and we say if x1 is 0, we go with this dotted line over here, and we write a 0 on it. If x1 is 1, we go to on a solid line over here, and we get 2 nodes of x2. Okay, again, let's say we have x2 and we have a 0, we go on the dotted line over here, or 1 over here, and we keep on traversing down this diagram until we get to the output level and see what the value of the function is. Let's take an example of, okay, this line, 0, 1, 0 equals 1. So again, x1 equals 0, so we go down over to here. x2 equals 1, so we go down over here. And x3 equals 0, we go down over here, and we see that the value of f is 1. Okay, another example, we'll take the last line, 1, 1, 0, and we should get an output of 1. So we start at the beginning, 1, 1, and 0, and the output is 1 as expected. So it's very easy to map one of these types of truth tables exactly to a binary decision diagram. Another important thing to notice about a binary decision diagram is that each one of these nodes actually has a tree under it. So if we were to now get rid of x1 over here and only look at x2 as the root of our tree, we can see that if x2 equals 0 and x3 equals 0, we get a 1. So we have 0, 0, that's x1, x2, okay, and f, we get 1. Right, and then we can go 0, if x2 equals 0 and x3 equals 1, we get 1. So 0, 1, 1. And then if we go x2 equals 1 and x3 equals 0, we get 1. So again, x2, did I make a mistake here? Sorry, that was x2 and x3, right? Okay, so if x2 equals 1 and x3 equals 0, we get a 1. And again, we go 1, 1, and we get a 0. So 1, 1, 0. And so we can see that that what we get here is basically a NAND gate. And you can, so that means that this node, if we start just looking at this node as the tree, we get x2, x3, not. So each one of these nodes basically is in the binary decision diagram represents a complete Boolean function, and we can actually describe many Boolean functions with just one BDD. Okay, you can also look here as a small example. If we look at this node, we see that if x3 equals 0, we get a 1, and if x3 equals 1, we get a 0. So that is exactly x3 bar. We can make many different things. If we wanted to show the actual BDD of the function 1, the constant 1, we would just put a pointer over, sorry, that's 0, a pointer over to one of these leaves of 1. Okay, that's a binary decision diagram. Another property that I just want to point out of the binary decision diagram relates to the Shannon expansion theorem. So the Shannon expansion of a function relates the function to its cofactors. Cofactors are also very important binary, computational Boolean algebra things that you can do, things like derive, put and find the derivative of a Boolean function with them. So if we have a Boolean function f of x1, x2, etc., in the middle somewhere we have xi, as you can see here. Okay, the positive cofactor, which would be called xi of 1, would be the function of all those same x's, but instead of xi, we would stick a 1. Similarly, the negative cofactor, if we have xi of 0, we would put a 0 here and find out what the function is. So those are the cofactors, and what the Shannon's expansion theorem states is that f is xi bar times the negative cofactor of I plus xi times the positive cofactor of I, or we can have a similar function down here. That's Shannon's expansion theorem. And why am I talking about this now? Because a BDD is exactly a representation of Shannon's expansion theorem. So look, we have f. F is pointing at our first variable at a, and what do we have over here? If a equals 0, then we get this function. If a equals 1, then we get this function. Well, look, if a equals 0, then we get, this must be the negative cofactor. Negative cofactor. And accordingly, this is the positive cofactor. So it's a very nice representation that can also give us the cofactors quickly of a Boolean function, and that is very useful for different things that we do in computational Boolean algebra. So there is a problem with BDDs. BDDs get very big. Let's see if we can provide a reduced representation. And amazingly, if we look at the BDDs, and again, on our last line, we have 2 to the power of n if we have n variables. So that's very big. That's really a big, a lot of data, a big representation, and we want to reduce this. we can take three very simple, I would call them, they seem almost trivial rules, and we can see we can get to something called a reduced order BDD. We can throw away a lot of those nodes in the representation. Okay, so our first rule for reduction is we're going to merge equivalent leaves. So if we saw in our picture before that we have these leaves, which are these squares, and remember they have either a 0 or a 1 inside, we're going to take all of the zeros and make them into a single square, and all of the ones and take them into a single square. And the arcs that pointed to our zeros, we're going to move all of them to point into the single zero that we'll have left. So if we look over here, we have this guy, this x3 is pointing to 0, and this x3 is pointing to 0 with a dotted line, and this x3 is pointing to 0 with a solid line. So we're going to take this guy and this guy and this guy and turn them into one square here, and then we're going to move this and this and this arc to point at them. Okay. Similarly, we have this, and this, and we see that this is pointing to it, this is pointing to it, this is pointing to it, and this is pointing to it. We're missing a 0 over here, I guess. So what we're going to do is we're going to turn all of those into a 1 and have everybody pointing at them. So that was kind of a very trivial, strange step, but it already reduced at least this line. So instead of having 2 to the power of n of these leaves, we only have 2 leaves here. We still have the same number of these arcs. So it probably didn't reduce much, but it will help us in a moment. So our second reduction rule, a bit more complex than the first one, but still pretty trivial. We're going to do what we call to merge isomorphic nodes. So if we have 2 of these variables that are at a similar level, so this is called x, could have been called x2 before or whatever, and we see that when this x equals 0, we go to y, and when x equals 1, we go to z. And this x also, when x equals 0, we go to y, and x equals 1, we go to z. We see that this and this representation of x, they exactly behave the same. So why do we need both of them? We will merge them. So we'll erase one of them, take the arc that was going into that one and push it into that one, and we don't have to do any, and we just delete these arcs because they don't exist anymore, and because what was happening from there is exactly the same as what was happening before. So that's called merging isomorphic nodes, because those nodes are isomorphic. So let's look at our diagram here, and we can see, for example, if we take this x3 and this x3, we look, and x3 equals 0, it goes to 1, and x3 equals 1 goes to 0. And again, x3 equals 0 goes to 1, and x3 equals 1 goes to 0. That means that these guys are isomorphic. We can merge them. So that means we're going to take these 2 guys and point there, erase that, and then we can erase this, and we're done. So what we get here is this 1 x3. Both of these x2s, you see there 1 arcs go to this x3, and the output of x3 is of course what it was here before. x3 equals 0, we go to 1, x3 equals 1, we go to 0. And now we have less nodes. Instead of having 4 nodes on this level, we only have 3. So we were able to reduce the size of our BDD. Okay, so our last reduction rule is we're going to eliminate redundant tests. This is another trivial looking thing, but again, it results in a large reduction of the size of the BDD, which make it a useful tool. So now we had this x that gets these 2 arcs that come into it, and 2 arcs that go out to it, and the 2 arcs go to exactly the same node. Well then, why do we even need this x? We can skip it altogether, and we'll just erase it, and we'll erase the arcs between it and move these guys to point down to here, and that's what we see here on the side. So let's look, for example, at what we have here, and you can see that this x3, both, it doesn't matter if it's 0 or 1, both of them are going to point to 1. So what can we do? We can get rid of it. We can take this arc, remove this, and just point this arc down to 1. Okay, and that's what we see here. We just pointed straight down to 1, and we skipped this node altogether. We were able to skip this one in a similar way, and you see that we were able to reduce our BDD to only have 4 of these internal nodes and 2 output nodes instead of the big tree that we had before. And that's on a small BDD, but if we would take something with a lot of variables, our reduction can be, at certain points, very, very efficient. Okay. So why are reduced order BDDs so important? Well, there are a few different things here. BDDs, it turns out, are canonical, or at least reduced order BDDs, excuse me, are canonical. In other words, what that means is that if we take a certain ordering, an x1, x2, x3 versus an x3, x2, x1, if we take a certain ordering, it doesn't matter what our start point is. If we iteratively apply our 3 reduction rules until we have no more reduction that's possible to do, we are going to arrive at exactly the same ROBDD for every starting representation of our function, no matter how many of these things we have. And that gives us a lot of cool things. However, it's important to pay attention that the ordering, again, is important. If we would change the ordering, we may get a better reduction or a worse reduction, and it's very hard to find, there are many heuristics to do it, but it's very hard to find the best ordering for a BDD, for a reduced order BDD, to get it to have the smallest representation in our memory of our computer. So some benefits that we can do, it's very easy to check for tautology. Okay, tautology means that a function is a constant 1. Well, we said before that the BDD of a function 1 is just this. This is the BDD of a function 1. Now, I said that a reduced order BDD is canonical. So once we apply our reduction rules, we're going to end up with this, despite the fact that we may have had a million variables at the input. And that's really cool. It's really easy to check for tautology, because all we have to do is apply our reduction rules on our reduced order BDD, and we will arrive at this type of representation, and then we know that the function is a constant 1. Okay, so it's very easy to do things like complementation of a function and equivalence checking. So for example, what we could do is we could take two functions, f1 and f2, okay, and we can just stick them into an XOR gate. And if f1 and f2 are equivalent, that means that what we will get at the output is a 0. And if they are not equivalent, we will get a 1. If it's a 0, right, that means that what we're going to have is, after we apply our reduced order BDD, we're just going to have something like that. So it's really easy to do this logic equivalence check, and this is one of the things that are used in logic equivalence checkers from commercial tools for formal verification. So just the final point is that I already mentioned before, that the size of a BDD can vary drastically if the order in which the variables are expanded is changed, and the number of nodes in the BDD can be exponential in number of variables, in the worst case even after reduction, so sometimes it is too big to use actually. Okay, but anyway, a BDD is something that you will probably run into in the future, and it's very worthwhile to understand the mechanics of it and know how it works. That brings us to the next part of the synthesis flow, which is constraint definition. So following elaboration, the design is loaded into the synthesis tool and stored inside a data structure. Now we have things such as hierarchical ports, inputs and outputs, registers, and so forth, and we can access them by name. And here's just a small example of some SDC commands or tickle commands that can be used to access these things. We'll learn about this in detail in the next lecture. Okay, we can load the design constraints now in what's called an SDC, or synopsis design constraints format, and we'll learn all about that. So we use a command inside genus called read_SDC, read_SDC minus verbose, and we point to this SDC file again, which we'll learn about the format. We'll learn about the different constraints and how to define them. I'm not going to do it now because they're very relevant for timing and so forth, but just believe me that there's these constraints for right now. For example, just the basic command that we're going to do is create clock, which will create the clock and define the frequency of the clock with this period thing, and the name of the clock and which port the clock actually is driven to the design through. Again, I'm not going to discuss constraints right now. I just wanted to point out that this is the point in the synthesis flow where we apply them, because now we actually have this structure. We know what the registers are because they were inferred and so forth, and so we can do different things like get ports and get cells and so forth. But again, we'll go into this in detail in the next lecture. So just one point, it's very important in the synthesis tool to carefully check that all the constraints were accepted, because if we made a mistake or so forth, we may not be constraining our design in the way we should have. So that leads us to the next stage of synthesis, which is technology mapping. So technology mapping is the phase of logic synthesis when the gates are selected from a technology library to implement the circuit. In fact, up till now, all we had was a generic representation. It could be in the form of just some sort of Boolean logic, such as a BDD or something like that. Or usually we take these generic gates and an OR and so forth gates that are inside the synthesis tool or inside the code of the synthesis tool, but they don't have things such as drive strengths, and they don't have, we don't know their size and so forth. They're just a bunch of gates that are representative, and they allow us to do the different multi-level logic optimization. Now we actually have to go to our standard cell library that we loaded it in library definition, or in the first part of this lecture, and we have to actually map our logic to these actual standard cells. So why do we need to do technology mapping? Why is this a very important, in some cases the most important point of our whole synthesis flow? So straight implementation not be good. If we just take these generics and put a gate there that we have in our standard cell library, we may not arrive at a good solution. For example, let's say we have a type of a function which is f equals a, b, c, d, e, f. That's a 6-input AND gate, but as we saw, we don't have 6-input AND gates usually in our standard cell libraries, because the higher the fan-in, the worse the gate is, and so we usually only have 4-input gates. Therefore, we have to actually make this into a different function, divided into several levels and so forth. And remember that we have all these gates in the library. They're pre-designed. They're usually optimized in terms of area, delay, power, etc. And we should find the way to do this most efficiently. So this is why we need to do technology mapping. The way that we're going to do technology mapping is to apply a minimum cost tree covering algorithm to solve the problem. And it's actually very cool. If beforehand we discussed heuristics, which didn't actually find us an optimal solution, but a good enough solution, in this case we're going to actually apply some optimal algorithms which will find the best solution under a number of assumptions. So let's go over the technology mapping algorithm. What we're going to do is we're going to use this recursive tree covering algorithm. Yes, recursive. Many of our algorithms in EDA are recursive, okay? And we can easily and almost optimally map a logic network to a technology library. This is done in 3 steps. The first step is what we're calling mapping the netlist and the technology library to simple gates. So what we're going to do is we're going to take our whole netlist, netlist of generic gates, and break it down to NAND2 gates, or 2-input NAND gates, and NOT gates, which are basic gates that are a universal set, and we can do that, and we're going to see how we're going to do that. The other thing is we're going to take the standard cell library, and we're also going to describe it just with NAND and NOT gates. So if we have some sort of other gate, we're going to turn it into 2-input NAND and 1-input NOT gates. In addition, for each of these standard cells, we're going to give it some sort of a cost, some sort of a number that will say how much it costs, that we can use this to minimize this cost function. Okay. The second stage is what we call tree-ifying. So tree covering, which is what we're doing, a recursive tree covering algorithm, only can work on a tree. Okay. A tree is something that has a root and has leaves, and each leaf only has one root, or the top of the tree, it only has a single parent. Okay, so what we have to do is we have to find all the places where we have a large fan out, because if we have a fan out, which we'll see in a moment, then we get more than one root for each leaf node. So we have to break this, and here's some sort of a level of lack of optimality, because what we have to do is break these at certain points with some sort of heuristic or decision, and then connect them together at the end, which I won't be discussing here, but there are algorithms and heuristics how to connect the trees back into one big tree. Finally, we apply this minimum cost tree matching algorithm, which recursively goes over the different trees that we made and puts and maps standard cells according to their cost. And yes, it does reach an optimal solution, at least for the inputs that we give it, which are these costs of each gate and these tree-ified input netlists. Okay, so let's go through these steps in an illustrative fashion. So the first step we said is simple gate matching. So what we have to do is we have to take our whole Boolean function, or our whole combinatorial network, and we have to apply De Morgan to turn it into 2-input NANDs and NOT gates. Okay, so this is the function that we arrived before at after we minimized our multi-level optimization with all these t's and f's and so forth. And what we're going to do is we're going to start applying De Morgan here, and we're going to turn each one of these t's into a bunch of NAND gates, or NAND and NOT gates. So we have bars here and we have NANDs. And so we can draw this on the outside as a whole bunch of NAND and NOT gates. So all of this stuff is now only NAND and NOT gates. And it's very important that we get it into NAND and NOT gates. Okay. The other part of our simple gate mapping is we take the standard cell library and we do the same thing. So it's obvious when we take a NOT gate, it just turns into a NOT gate because that's only described with a NAND and NOT gate. And we also give it a cost. So this inverter, we gave it a cost of 1. Okay. Then we look at, for example, this 2-input NAND gate, and we can also describe it just with a NAND gate. So a 2-input NAND gate turns into a NAND gate, and we decided that its cost is 2. Well, we have this NOR gate, and for example, just as a type of a study, you could say that in CMOS, a NAND, a 2-input NAND and a 2-input NOT, they're kind of inherent to CMOS. However, to turn a 2-input NOR gate, to turn a 2-input NOR gate into a bunch of NANDs and NOTs, we have to do some sort of De Morgan, and we get this 3-level logic, 3-stage logic. But since it's internal or inherent to CMOS, we can also give it a low cost, for example, 2. Then we take these other gates and we again have to apply De Morgan and map them just into 2-input NANDs and NOT gates, and we'll do that, and we'll give each one of them some sort of a cost according to the complexity of the gate or some other metric that we applied. Again, how we give these costs, that's actually an art, and it's not something that's optimal. It's something that's done according to all kinds of heuristics and according to all kinds of decisions and so forth. Maybe how we characterized our lib files depends on maybe on size, maybe on power, etc. So these are just numbers that I'm giving as an example. They're not something that is straightforwardly calculated. So remember, in our tree covering algorithm, this is an important input, the cost of each gate, and it can lead to lack of optimality. So that was our simple, our simplifying the netlist. Now we go into the second stage, which is tree-ifying. So again, we can have any given logic network, and this is a logic network. And what we want to do is we want to see that each output has a bunch of inputs. That's what a tree is. So the output is the node or the root of the tree, and each of these inputs are the leaves of the tree. And we want to take some sort of input, such as this guy, and we want to trace through the tree. So if we trace through the tree, we can go and arrive at an input. And that's wonderful, actually, because we see that each node has a single root. But if we take, for example, this guy here, and we go and we start to traverse the tree, we reach a junction. And that's not good, because maybe this is the root of the tree, and maybe this is the root of the tree. Therefore, this is not a tree structure, because this input, for example, has 2 optional parents. Okay, so what are we supposed to do? We have to break the tree in a way that where there's a fan out of 2. So that happened because this NAND gate had a fan out of 2. So what we're going to have to do is we're going to have to break this guy. And what we arrived at is 3 trees. We have this tree, which is completely and totally a single tree where every input has 1 output. We have this tree, and we have this tree. And once we did that, we can go and optimize each one of these trees. So that stage is called tree-ifying, and we have to go through the whole design, cut the fan-outs that are higher than 1, and turn it into separate trees, and then apply our tree covering algorithm to each of these 3 trees. So that leads us to our third stage, which is the minimum tree covering stage. So we can apply the recursive algorithm to achieve the minimum cover. Let's see how this works. We start at the output of the graph, or the root of the tree, which we call I over here, and we see that there is some sort of a logic gate that is driving the output, and the logic gate has a bunch of inputs. Okay, what we're going to do is recursively, we're going to look at each input of the logic gate that is at that is driving that output, and we're going to find all the matching target patterns that we could have covered each of these input trees, because each of these is also a tree in itself. Okay, and then we're going to figure out or calculate what the cost of node I is, and the cost of this node here is the cost of the gate, okay, plus the cost of this tree plus the cost of this tree. That's the cost of this node, and that's a recursive function, okay? And what we're going to do is we're going to try to find the minimum value of that. And if we find the minimum value of that, we have the minimum value of the cost at node I, which if we apply the same algorithm, for example, to node K1, then we'll find the minimum value of K1, and obviously that is part of the minimum value of I, because again, this is a tree, there are no branching out to other trees and so forth. So for simplicity, we're just going to help us in the illustrations on the next slide. We're going to redraw our graph, just use different symbols for how we show things. And we're just going to use a circle, an empty circle with an I inside to represent a NOT gate. This guy's a NOT gate. Okay. And we're going to have a N inside a full circle, and that's a 2-input NAND gate. Finally, we're going to have a box that represents each input. So the input to an AND gate, if this was A, we're going to draw a little square with an A inside it. Okay, so let's see the example of how we do this. We're going to take this tree over here on the left. The tree has a root node, which is called F, and it has inputs A, B, C, and D. What we're going to do, and remember, we've already simplified this, so it's only a bunch of NAND gates, 2-input NAND gates, and NOT gates. Okay, we're going to take our representation, and remember, this guy should turn into an I like that, and this guy should turn into an N, which is filled in, right? That just helps us look at it. And so this is our basic representation of this tree, and these are equivalent to each other. Another thing we did is we took each of these gates. It's actually each of the outputs, right? These are the I's on the previous thing, each of these outputs, and we gave them letters. So this was called F, this one W, Y, Z, X, and each of the inputs we put inside a square here. The other thing, we have to simplify the standard cell library. So we have over here our standard cell library, and inside we have a NOT gate, a 2-input NAND gate, a 2-input AND gate, a 2-input NOR gate, and an AND or invert with 2 inputs and 1 output over here. And we used De Morgan to turn them into a bunch of NAND gates and inverters, and we gave each one of them a cost. This cost is just for the purpose of the example. Again, deciding on this cost is a very important part that can lead to lack of optimality, because now our minimum tree covering is going to be optimal given this standard cell library, given this net list, and given these costs. Okay, so what are, just to point out, right, this is an inverter. It has an inverter and 1 input. This is a 2-input NAND gate. It's a NAND gate with 2 inputs. This is an AND gate because it's a NAND gate that drives an inverter, and the NAND gate has 2 inputs, and so forth. So these are just the NAND NOT representations of our standard cells. Okay, so now what are we going to do? We're going to start at the top. We're going to start with node F, and remember, this is recursive. We're going to say node F should be the minimum of the cost of the gate that we're going to put there, plus the cost, the minimum cost of all of the node at the input of node W. So what we're going to do is we're going to check which patterns match. And we look at our standard cell library here, and we see that only this guy has actually at the top of it an I with 1 input, which is what fits over here. So only this has to be a NOT at the end. That's the only standard cell that fits. Well, that's not exactly, but it sure does fit. Okay, so we say if we put a NOT at node F, then the NOT has a cost of 2. So we write 2 here, and we say that the minimum cost, if we decide to put a NOT gate here, is 2 plus the minimum of however much the minimum cost of node W is. So we write that down. If F is implemented with a NOT, then the cost is 2 plus the minimum of node W. Well, we look along at our standard cell library, and we see that this doesn't fit node F, but hey, what happens if we put this I here over here? It's connected to an N over here. That looks like it should be, and this has 2 inputs. Wow, this AND 2 gate could also be stuck here and covered on our tree here. So if we decide to put an AND 2 gate there, the cost of the AND 2 gate is 4, and we have to add to that the minimum of the cost of node Y and the cost of node Z. Okay, so that's another possibility we have. What other possibilities do we have? Could this fit? Let's see. It's an inverter that goes into an AND gate, and it has on one side an inverter, the other side an AND gate. That does not fit a NOR 2. So we can't use the NOR 2, but how about our AOI? An inverter, a NAND gate, one side an inverter, and the other side an AND gate. Look at that. We can use our AOI to 1 to cover all these 4 nodes. So let's take that into consideration. If it's an AOI 2-1, that gate costs 6. And we have to look, the minimum of Y is 0 because A is the input. The minimum of B over here is 0. But the minimum of this node is the minimum of X. So we get to 6 plus minimum of X. Okay, we finished with node F, but now we have to find out what all these minimums are. So we go down to node W. So let's look at node W. Node W has an AND gate over here. And if we look at our standard cell library, it's easy to see that the only thing that could fit is this NAND 2. So that's our only possibility actually to put it W. So the cost of W, if we implement it with a NAND 2 gate, is 3 plus the minimum of its 2 inputs, which are Y and Z. There are no other covers that could be possible at node W. So let's traverse down into node Y. Node Y has an I here, and we look, well, it only has A at the input, so the only thing that it could possibly fit is this NOT gate. Not only that, the NOT gate doesn't have any logic that goes under it, and the cost of A is 0, so we know that the cost of Y is 2. That's the minimum cost of Y, and we have to put a NOT gate over there. Next, we go over to Z. Okay, Z, again, we have an N over here at the top, and we look around, and the only thing with an N over at the top in our standard cell library is this NAND 2 gate, so we can only implement it with a NAND 2 gate, which costs 3 plus the minimum of this node is 0, and the minimum of X. So Z would be applied with a NAND 2 gate, costing 3 plus the minimum of X. Again, we go down to X, and we get the same thing, and X has to be applied with an AND gate, so its cost is 3. So X costs 3. And then we can start going upstream and figuring out what the cost of each one of our nodes is. So we see that X costs 3, right? And we see that Z costs 3 plus the minimum of X. The minimum of X we just found is 3. So this costs 3 plus 3. That equals 6. So we see that Z equals 6. Now we go up to Y. Y we already saw it equals 2. And we can traverse up to W. W costs 3 plus the minimum of Y. The minimum of Y we see is 2. And the minimum of Z is 6. So 3 plus 2 plus 6 equals 11. So we see that the minimum cost of W, is 11. Okay, next we go, and if we would have mapped the whole thing, just the F, to a NOT gate, right? Then we have 2 plus the minimum of W, 2 plus 11. That would equal 13. So one possibility, if we would put a NOT gate up here, right, we would get to a cost of 13. Okay, the other possibility is to take an AND gate here, put it on these two guys. In that case, we have 4 plus the minimum of Y, which is 2, plus the minimum of Z, which is 6, and we get to 12. So if we would have put an AND gate over here, we would have had 12 as the cost. Finally, we can look and see what would happen if we would put an AOI that would cover all of these guys. And we see that the AOI costs 6 plus the minimum of X, which is 3. That means we arrive at 9. And that is obviously the minimum of all these. So what we want to do is we want to use an AOI. In the case of the AOI, we cover all of these guys with this nice AOI gate. And we do the minimum of X. So we look, X should be with an AND 2 gate. And so we are able to cover this with a minimum cost. So that is how we do our technology mapping, and that allows us to move from our generic standard cell library into a technology-dependent standard cell library, and using our specific standard cells that are right for us. So just going into our little break for a moment in our lecture, we'll look at our Chip Hall of Fame for this week. And we're speaking about synthesis, right? So we'll go into a very famous synthesizer, and it's not a logic synthesizer, which we're learning about, but rather a speech synthesizer. And this is the Texas Instruments TMC 0281 speech synthesizer. Here's a picture of the chip on the bottom right. The reason that this became very, very popular is because it was used in the Texas Instruments Speak and Spell machine, which you can see here being held by our friend E.T., or used by E.T. to make his communication system that he phoned home with. But also, first of all, the Speak and Spell, which used to talk to you and say, can you spell this or that, was a very cool machine that when I was a kid, everyone had. And it actually used this chip, which was able to use a bunch of buzzing, hissing, and popping sounds in order to make sound. It was released in 1978. It had a 44 millimeter chip size, and it was inducted in 2017 to the IEEE Chip Hall of Fame. By the way, it was considered for a long time impossible to even make speech with just by using synthesis. In other words, putting in some sort of a word and having a machine make the sound. But eventually, in the late 70s, they were able to do this with different speech synthesis chipsets. And for the 0281, it was the first single chip speech synthesizer, and it became very popular. Okay, now that we know how synthesis basically works, we can go revisit how we write Verilog for synthesis. So there are some things that we may have missed. We now see how synthesis works, so let's revisit some of the things we may have skipped or briefly mentioned earlier. For example, let's take a 4-to-2 encoder. Remember that what an encoder does, it takes a one-hot encoded vector and outputs the position of the 1 bit in binary encoding. Okay, so one way we could possibly write this, and I'm just going to show you how different ways of writing our Verilog could affect things. Okay, so we can write always at x, begin, encode, that's just the name of the block. If x equals 0001, then we'll output 0 for the 0 position of the 1. If it equals 0010, we'll output the 1 position, 100 the 2 position, and 100 we'll put out the 3 position. If not, we'll propagate an x. Okay, so what happens when we actually synthesize this? The synthesizer has to adhere to what we wrote here. And we see that there's precedence. It has to check this condition before it checks all the rest. That causes what we call priority logic. As you see here, we have to check this 0001 going into a multiplexer, and we have to check that before we check 1000, and it makes the synthesizer put this type of a structure out. And the reason is that that's what we told it to do. It has to check all this in a sequential fashion, so this has to happen before this, and that causes this thing called priority logic. That may be something we wanted to do, but often it was by accident. If we had used the case construct, for example, we'd have always at x, right? Case x, and then we have all these options. Cases are usually parallel. You can also tell the synthesizer in various ways, such as pragmas or in certain options inside the synthesis tool to relate to this is in parallel, but usually they're taken in parallel. So if we did that, all of these things are equal and in parallel, and we get this type of a logic if we go and implement what it says. Now, is that good or not good? Well, the synthesizer can look at this and see that it can actually really cut down on the logic and optimize it to be just type of an AND gate and an OR gate, and that's much smaller than the logic we had in the priority logic, achieving the same thing. We could have also written it a bit differently. For example, let's say what would happen if we could guarantee that the input was one hot encoded. We know it's one hot encoded because say our logic wouldn't allow it to be something else. Then we could just write the code differently. We could write just looking at the single bit, if x0 or if x1 or if x2 or if x3, and that could bring out different type of logic. Again, this is priority logic because we're looking at x0 before the rest, and we get what we call a priority decoder. Okay, you see that we have we look at x0, but we don't look at the whole vector of x. We can look at one bit and we get much smaller logic, and we get this bit gets significance over the others. So that's something we might want to do. Okay, let's look at the operators that we used in Verilog. Remember that logical operators map into primitive gates. So if you use an OR, like we do in assign A or B, it'll just turn into an OR gate, and that's very nice. But arithmetic operators, they map into different things. Adders, subtractors, these things are big. They can be unsigned 2's complement. They have to take into account carries, right? And then if you write something like a multiplier, then it's going to be a big multiplier. So it's not that trivial, and it's much better to do it if you can stay away from it with all kinds of shifters and things. And if you write modulo or divide, that's going to be a bigger problem, because modulo and divide are really non-trivial types of implementations. Okay, relational operators, bigger than, smaller than, etc. They make comparators. Comparators, again, these are a type of like an adder or subtractor, and so they're going to be big. Now shifting. Shifting is interesting because if we shift by a constant amount, look, this is a shifter that shifts by 2. All it does is it makes a connection between the input bit and the output bit, and that does the shift. That's because it's by a constant value. So this is very cheap logic. But if we have a variable amount of a shifter, we need a shifting module, and that's another big arithmetic block. So if you can turn it into a constant shifter, please do. Okay, conditional expressions like an if or a case, they obviously make logic such as multiplexers. Data paths are very interesting and important. So adders and multipliers and so forth, as we said, they're complex. They have a lot of meaning, and you probably learned in a previous course that there are different ways to do this. For example, a multiplier, it could be made with a Wallace tree multiplier. It could do Booth recoding. It could use a carry save adder array. There are lots of ways to do this. And in most of the tools nowadays, what happens is that you get these IPs, these pre-written kind of structural descriptions of how to make these different types of architectures, and the synthesizer will either choose one of them for you according to the different constraints that you enter into it, or you can actually explicitly tell it to use one type or another. These in Synopsys are called designware. They're kind of the father of these types of IPs that they're soft IPs that you can use to implement. Cadence calls theirs chipware. So these are types of things that you should use, you should be aware of. You can look into the user manuals of designware, chipware, or whatever other companies provide, and see how to instantiate them, see how to use them, and see what actually the synthesizer decided to use in implementing these things. A very important point, and I decided to put it here, is clock gating. So the clock is continuously toggling. It has a very high activity factor, and so it's a major consumer of dynamic power. Therefore, in order to save power, we will try to turn off the clock for gates that are not in use, and that's called clock gating. So we have two ways of doing basically clock gating. If we know that a whole module is not working, we can do what is called block level or global clock gating. Okay, so we can just put a clock gate in that we instantiated or put it in our RTL, and we can decide that we don't need to use, if a certain mode wants to turn off a certain block, we just gate the clock. It will never be used. The clock won't get into the block, and nothing will actually change in the state, and our clock tree also won't be wasting power. That's one level. It's a very coarse level. There's another level that's local clock gating or register level clock gating. We can see in a second how we can implement for each and every register. We can check if we can put a clock gate in certain conditions. So what are those conditions? Well, if we have an enable condition. So for example, here we have a D flip-flop, and what happens is we have some sort of enable condition that says that if enable is 1, then we should take D in and propagate it to D out. But if enable is 0, what we should do is just resample our original signal. That's just like an enable flip-flop. Okay, if we take this thing and instead remove this multiplexer here and replace it with some sort of a clock gate, for example an AND gate, we can stick the enable into the AND gate, and the clock will only propagate to the pin here once enable is 1. So therefore, we saved the toggling on the clock net. This will save power actually inside the flop, and we'll see in a moment we can share this between different flip-flops. So that's how we do local clock gating. There are 3 methods, in fact, to do local clock gating. On the one hand, we can use the logic synthesizer to find and implement local clock gating opportunities. So if we just write a flip-flop always at pos edge clock, if enable q equals the in, then what can happen is the synthesizer can run over this code and see, aha, I see one of those examples like we saw a minute ago, an enable flop. I can remove the enable and instead use a clock gate. Remember, this is not Boolean equivalent, but it has the same functionality. A different way is to do it with RTL code, where we can explicitly specify clock gating. So we can assign gated clock equals enable and clock, and then always at pos edge gated clock. So we only propagate the gated clock into a flip-flop that doesn't have enable in it. A third way is to explicitly instantiate a clock gate in the RTL. So we have this module called clock CLKGX1. We can instantiate it, give it an enable signal, a clock, and the out of it is a gated clock, and put that in the flip-flop. So that's another way to do it. We can also do some of these at the global method. One is using this RTL code, and the other one is instantiating a clock gate. Often we'll use the instantiation actually of a clock gate, because that way it's easy to tell the synthesizer not to remove it and to keep it there, even though it may not look like it has any reason to be there for some sort of a synthesis algorithm. But maybe I was lying to you, because what happens if there's a glitch on the enable signal? Look, we have this AND gate here. Glitches on AND gates can propagate. So let's look at what happens here. And we have our clock signal, we have our enable signal, and let's see what happens with our gated clock. So the clock went down here, and there was a glitch on the enable signal, and lo and behold, nothing happened to the gated clock signal, so we were fine. And as I say here, we live in a perfect world. We get a little smiley face, and it's even green. However, not so fast, my friends. What happens if the glitch happened during the high phase of the clock? And that's where a real sorrow happens. Because if the glitch happened here, what happens is this AND gate propagates the signal to the output, and we get a fake clock edge on the flip-flop, and that's really bad. In fact, it's so bad that we can't actually use such a structure. So what do? Luckily, long time ago, our forefathers found something called a glitch-free clock gate, and it's basically taking a latch here with a negative edge latch, a negative level latch, and connecting it to the clock signal, and the enable goes through that before connecting to the same AND gate we had before. We can also describe it here in RTL. However, this is usually what we call an integrated clock gate, and it's provided in our standard cell library. So let's see what happens with this. We have our same clock, and just to see that we're not doing anything during the low edge of the clock phase, enable changes during the low edge of the clock phase. And what we see here is that enable out, this signal over here, it basically follows whatever happened at D, right? Because this is a negative latch. When clock is low, then this latch is transparent, and enable out goes low. Did it cause some sort of glitch on gated clock? No, because clock was low, and therefore through an AND gate, gated clock was low, so any change on enable out didn't actually do anything to us, which is the same as just putting an AND gate over here. So it was fine that we propagated our enable out signal during the low phase of the clock. So what happens if we have our glitch on the high phase of the clock over here? Well, at that time, our latch is actually opaque, and then the D will not be traversed, will not be passed over to the enable out. Enable out will stay stable at 0, and our gated clock signal will stay stable at 0. So this solves our problem, and this is the type of a clock gate, either using an integrated single standard cell, or by writing our RTL in this way, we get this type of a structure. We can merge clock enable gates. As you saw, putting a latch and AND gate is kind of expensive. Latches are big. So what we can do is we can find all kinds of places where the same enable signal goes to multiple flops. If the same enable signal is going to multiple flops, then we can just use one clock gating cell, providing the gated clock, and then pass all those gated clock to all these flops, and then the extra area of this latch or this integrated clock gating cell is divided among all those flops, and that's usually what's done. We can usually tell the synthesis tool what our threshold is of how many flip-flops that have to share an enable signal in order to use this clock gating, or else it's too expensive to do. Another type of gating is data gating. Clock gating is very well understood and automated, but there's another thing that happens on data signals that we can also sometimes save power. There are different heuristics and algorithms to look for data gating, but it's not as trivial and straightforward as clock gating, and we should write our RTL with this in knowledge to try and keep our power low. So for example, here's a kind of a simple example about this type of a thing. We have some sort of an ALU, and it has a shifter and an adder inside, and we have this signal called shift add select, which selects either to output the shifter output or the adder output to the next level on. We also know from our block that we barely ever use the shifter. We're usually using the adder. The problem is that every time that A and B change, we calculate this addition, which wastes power in the adder, and we calculate the shift, which wastes power in the shifter. And usually we're not using the shifter, so that's kind of ridiculous to do. So instead of that, what we could do is put a data gating AND gate on the entrance to the shifter, and then as long as this select is selecting the adder, the inputs to the shifter will be 0, and we won't waste any power on changes due to A and B changes on the shifter. So that's the type of a thing that we could do. Point about that is what's called a linter. So there's a linting tool or a linter. I'm not sure exactly where the word lint comes from. Maybe it's for cleaning up lint like in your laundry, but it is something to find all kinds of problems with how you wrote your code. It finds things that could cause problems in simulation and synthesis, things that could cause mismatches between simulation and synthesis, places where you could put a clock gate, places that will cause latches to be inferred, clock domain crossing issues, and all kinds of strange assignments and bit width and stuff like that. Actually, these type of lint tools, they usually output lots and lots and lots of warnings, and a designer will have to go through them and kind of try to clean out their log files, because many of the things were done purposely, but sometimes it can pick up some really bad problems. Note that it's not for checking syntax. Your simulator will already check syntax if you're missing a semicolon or something. But I just want to mention that some of the synthesis tools, maybe even some of the simulation tools, will already give you basic lint warnings, such as is done in Genus with some of the check design tools. For our final section in this lecture, we'll go into timing optimization. So how can we optimize timing? There are actually many transforms that the synthesizer can apply to the logic to improve the cost function. Resizing the cells, buffering or cloning to reduce load on critical nets, decomposing large cells, swapping connections on commutative pins, moving critical signals forward, adding early paths, recovering area. There's a lot of stuff, a lot of different heuristics that the synthesizer applies. Let's take a simple example. So we, after doing all kinds of synthesis and technology mapping and so forth, we arrive at this type of a net list, and we see here that these two inverters are in line, and they actually aren't doing anything. They're just buffering a signal, so we can remove them possibly and maybe save some time, because the delay here had these two gate delays where the delay here doesn't have any. That's just a really simple, maybe trivial example, and it may not be correct depending on the load and so forth. But let's see a few of these heuristics that are actually useful and optimized. So we'll start with resizing, cloning, and buffering. Resizing, it's also one of these basic straightforward things. We have this NAND gate, and we have a lib file of the NAND gate that describes how it works. And we have three different NAND gates. We have a red one called A, size A yellow one size B, and a green one size C. And what we can see here is that we have output loads that equal to 0.7. So if we go down to 0.7, we can see that the green one will have about 0.25 or so, and the red one will have about an 0.35 delay. So obviously with such a load, what we should do is we should take the green cell, the C cell, and we'll get a better delay. So just by resizing and changing the size of a certain driver, we can get better timing. That's pretty straightforward, but we can also do things such as cloning. So we can take the same type of situation. We have our NAND gate here. We have our load, which is quite large. What we can do is we can just make another copy of our NAND gate and have each one drive part of the load. That's called cloning, and you'll see in your synthesis tool that it says such and such a gate was cloned. Obviously, we can also buffer the fan-out net. So doing the same, instead of actually cloning and making another copy of the NAND gate, we can have our, depending also on where the things are placed in the end, we can have some of these capacitances sitting off of the same net, and some of them going through a buffer which can strengthen the signal and better drive the rest. So basically this NAND gate is now driving 0.5 versus this one is driving 0.6, and maybe that gets us a better balance. So those are the basic 3 ways of doing logic optimization or timing optimization, but there are many more. So for example, we can redesign the fan-in and fan-out trees. So let's see what redesigning the fan-in tree is here. Our timer sees that these 4 signals arrived at different times. This one took the longest. It took 4 whatevers to arrive, and this one arrived immediately at time 0. And if we look at this, our worst case path is through here. So we went through A, right, and it took us exactly 6. We arrived at E after 6. Well, looking at that, we can just redesign our fan-in and improve this. So we took C and D, which arrived at 0 and 1, and for example, C, which is the worst case of that, it went through these 3, and it arrived after 1, 2, 3, 4. Okay, that's fine, but looking at A, which came at time 4, it just went through 1, so the arrival time at E is eventually 5. So we were able to reduce our worst case arrival time from 6 to 5 just by redesigning the fan-in tree without changing any of the logic. Redesigning the fan-out tree is a similar type of a thing. So if we look at here, our longest path is from our AND gate through this inverter, through this 4-input AND gate, which has a large delay, and that took us 5 time units. Well, we can redesign the fan-out tree in this way. We can take our AND gate and directly connect it to this AND gate, so our arrival time through this path will now be 4. On the other hand, we can stick some sort of a buffer that it separates our load over to here. We can make it even a bigger buffer, and then it drives these guys. If this buffer had a delay now of 2 because it has a larger fan out, then this takes 1, 2, and 3. So we get another arrival time at 4, and we balance these 2 to be 4 instead of being 5 as we had before. So that's another way of restructuring the fan out to achieve better timing. Of course, we didn't change the logic here. Another way to do things is to decompose and swap. So obviously, and we've learned about this before, we can decompose complex gates into less complex ones. So we have this 6-input AND OR gate, and we can decompose it in several different ways. We can turn it into 2-input NANDs with a 3-input NAND on the output, or we can make it entirely with 2-input NANDs, and depending on what we want to drive, we can arrive at the best logical effort or whatever to do this in the best way. Another thing is we can swap commutative pins. So this is a simple sorting type of thing, and it's based on the fact that not all pin delays are the same, and not all paths through the logic are exactly the same. So again, we have these arrival times. So this signal arrived at time 0, and this signal arrived at time 2. And our worst path is obviously from the one that arrived at 2. It went through this really bad 2 delay gate, so it arrives over here at 4. And another one, we arrived in the end at time 5. We can just swap pin number C and number A. So we just did a kind of a shifting over there, and now the latest path arrives at number C, goes through another one, and it took 3 time units. Our fastest delay was at A, which took 0, so now it went through 2 and another 1, and it also arrived at 3, and we reduced our timing from 5 to 3 just by swapping which input, and these are all commutative. They do exactly the same logic, so it didn't matter to us. So that's another type of timing optimization we can do. The most complex type of timing optimization, it's often something that designers are very scared of doing, in fact, is to do what's called retiming. Retiming is something a bit more complex. If we're given the following network, so we have some sort of a pipe with registers, you see that this is 6 plus 4 plus 2. That takes 12 time units to go between flip-flops, versus this timing path has 4 and 4. It takes 8 time units to go through. And we want to arrive at a cycle time of 10, but that's impossible because this took 12 time units to go through. So what could we do? Well, in certain cases, the synthesizer can go over this logic, and it can just move, for example, this buffer over to that side, and you see that what we get is 10 over here and 10 over here, and then our worst case timing path between all flip-flops is 10. The problem is that now this logic cloud is different than this logic cloud, and this logic cloud is different than this logic cloud, which makes things such as equivalence checking very tough and non-trivial, and therefore sometimes this is stayed away from, but it's a very strong type of a tool that you can use to balance different timing paths and reach a higher throughput in the end. So that's the end of our 2 lectures about logic synthesis. A lot of all the algorithmic stuff basically was taken from Rob Rutenbar's wonderful Coursera course. I took some stuff from IDESA, which has a great set of courses to learn how to do things. Of course, John Rabai's low power design essentials and other types of things that I was able to find around the internet. Thank you.